Hello everyone, we are group 3 of EC doing case study on Fourier transform and its theorems. First we will look at a problem about Fourier transform. Here it goes. Find the Fourier transform of x of t which is equal to e power minus modulus of t for which the t lies between minus 1 and 1, otherwise it will be 0. Now we will see the solution for this problem. We know that the Fourier transform of x of t is equal to x of j omega and e power minus modulus of t is equal to e power minus j omega t. We are going to substitute it first. After that, we will get it as minus infinity to plus infinity x of t into e power minus j omega t into dt. By considering infinite intervals, we can't get the solutions, so we are taking a finite interval as minus 1 to 0 e power t minus j omega t into dt plus 0 to 1 e power minus t into e power minus j omega t into dt. Now we will get it as, here the bases are common like e power t and e power minus j omega t, so we are going to add the powers. We will get as e power t into 1 minus j omega dt plus e power t into 1 plus j omega into dt. By doing integration, we will get it as e power t 1 minus j omega into dt. If you are taking integral, it becomes e power t into 1 minus j omega by 1 minus j omega. Same it goes here, e power minus t into 1 plus j omega by minus 1 plus j omega. Limits from 0 to minus 1 and 1 to 0. By substituting upper limit minus lower limit, we will get it as 2 by 1 plus omega square minus e power minus 1 e power j omega by 1 minus j omega plus e power minus j omega by 1 plus j omega. By simplifying it, we will get it as 2 cos omega minus 2 omega sin omega. This is the solution for the first problem. Now we will look at the theorem regarding Fourier transform. Here we are going to prove the linearity and Poisson theorem of Fourier transform. First, we will see about linearity theorem. If we are considering the Fourier transform of x of 1t is equal to x of j omega and f x of x2 t into x2 of t is equal to x2 of j omega, then by linearity theorem we can write it as a1 x1 of t plus a2 x2 of t. Here the a1 a2 are constants, so by taking Fourier transform for this, we will get it as a1 x1 j omega plus a2 x2 j omega. By taking integral for this, we will get it as a1 x1 j omega plus a2 x2 j omega. This is the linearity theorem. We have proved it by Fourier transform. Now we are going to see about Poisson theorem. It is also known as energy density spectrum. Here it formula goes by L is equal to minus infinity to plus infinity modulus x of t the whole square into dt, which is equal to 1 by 2 pi minus infinity to plus infinity modulus x of j omega the whole square into d omega. Here it is the formula for Poisson theorem. We have energy. Fourier transform of energy is equal to minus infinity to infinity modulus x of t the whole square into dt. If we are going to simplify this, last we will get it as minus infinity to infinity x of t into 1 by 2 pi minus infinity to infinity x into j omega into e power minus j omega t into d omega into dt. By considering infinity to minus infinity to plus infinity x of t the whole square into dt, you will get it as 1 by 2 pi minus infinity to plus infinity x into j omega d omega. By simplifying it as by traversing order of integration, we will get 1 by 2 pi minus infinity to infinity modulus of x j omega the whole square into d omega, which is the Poisson theorem formula. Here The x j omega modulus whole square defines the energy density spectrum of a signal x of t. So we have proved the Fourier transform using Fourier transform, the linear and power cell theorems. That's all about our case study.